So let's look at another very cool extension of the ideas of complex numbers. I want to go back to the simple version of our motivating problem, y double prime equals lambda y, where lambda is some number. And I want to point out a similarity to, this was in number 3 just a couple of videos ago, this idea of an eigenvalue and an eigenvector. And this is just pure linear algebra, that I have some vector and a fixed matrix, or I have a fixed matrix, and I want to find some vector and a number lambda that satisfy this, and where v is not equal to 0 to make it non-trivial. And this is called an eigenvalue, and this is called an eigenvector. Well, there's some obvious similarities, and you can take this problem and turn it into this problem in some situations. But I want to say they're actually the same problem. This is just, if you put it in a general enough framework. Instead of the objects of interest being vectors, which you can add to each other and multiply by scalars, the objects are functions, like a mystery function y. And well, you can add those to each other and multiply them by scalars. So they form what's called a vector space. And it's not important to talk about the total abstraction and rigor of that, but just to say that there's this analogy that can be made totally precise. And in particular, let me just rewrite this as, I'm going to write this in this way. I'm going to say delta of a function y. Delta is an operator, some machine that eats functions and spits out functions. And for reasons we're going to see, it's going to be negative y double prime. So it's the thing that does negative the second derivative. And you might wonder why the negative, and we'll see. Okay. And then what this says is we're looking for, and so I'm going to just look for delta y. I'm going to change this slightly. I'm going to put a negative here. I'm going to look for functions y, mystery functions y, so that when you delta them, in other words, take negative the second derivative, you get just a scalar multiple of that same function. And what the negative is going to do is going to turn out that means these lambdas are going to be non-negative in a certain situation. And that's going to be nice because then you can take square roots easier and things work out in a prettier way. Now, the thing about this problem, and again, I didn't hardly talk about this at all, it turns out that it's rather special when this happens, and there's only a few lambdas for any particular matrix. There's only a few lambdas at work. And what I claimed was that the things that make, in that situation, they're the things that make determinant of a minus lambda I equals 0. And we find those by solving a polynomial equation. You can't just pick the lambda at will. Now, in the situations we've had already, we did pick the lambda at will, and it didn't matter. Like the spring constant, for example, could be whatever. There weren't only some special springs for which this worked. Well, here's a problem where lambda really does have to be special. I'm going to look at this, and I'm not going to put in initial conditions. I'm going to put in what's called boundary conditions. And I'm going to say y of 0 and y of pi are both 0. So I'm looking at and let's say t is our independent variable. So I'm looking at some function such that second derivative is a multiple of itself, and I've just incorporated a minus to be kind of clever about it, and it goes from 0 here at t equals 0 to pi, okay? And what kind of thing can that look like is the question. Well, it's easy to solve that problem because we already know what the general solution is using our magic of complex numbers, or just thinking about what happens with just even at the very start of this whole series of videos, we knew the answer. We had a guess. Okay, it's y of t is a cosine, and here is where it's nice. We don't have to have a root minus lambda. It's root lambda. Okay, and you can check that if you take the second derivative of this, you get a minus, because that's how cosine and sine work when you take second derivatives, and then root lambda comes out twice, you get a minus lambda. This does satisfy y double prime is minus lambda y, or in other words, this delta thing, delta y is lambda y. Okay, but what about the initial conditions? Okay, the boundary conditions. Y of 0, okay, that's going to die, and that's going to be 1. That's a, that's supposed to be 0. So in fact, we don't want the cosine, which makes sense. We want this function that starts here. Cosine starts off the axis, okay? And then y of pi, okay. Well, now it's just this guy. It's just b sine root lambda pi, and that's supposed to be 0, okay? Now, we could have b equals 0, but that would be stupid, because then this whole thing would be 0. And just like in the linear algebra case, we don't want y to be the actual 0 function. That's just totally useless and was an obvious and uninteresting solution. So that means this guy has to be 0. That says something about lambda. Okay, it says that root lambda, well, let's see, what kind of thing sine something times pi is 0? Oh, it's integers. Sine vanishes at exactly the integer multiples of pi. So root lambda has to equal, let's say, k, or in other words, lambda equals k squared. Okay, and so in other words, lambda equals 0, 1, 4, 9, etc. And notice that those are non-negative numbers. And that turns out to be a very nice thing. Even though the whole point, you could say, about all these videos is taking the square root of negative numbers, it's nice to not have to if it's not forced on you. Okay, so what's the relationship to what we were doing with complex numbers? There's this wonderful story. This is a very general story, and I'm not going to be very precise about this, but you have this operator, delta in this case. It goes from the set of functions, it takes a function as an input and has a function as an output. Okay, and it doesn't understand how to do it with any function. They have to be differentiable, but I'm not going to worry about that. And it takes y to minus y double prime. Okay, and the set of eigenvalues of delta, that's called the spectrum, because it has a very direct relationship to spectroscopy of look at the colors emitted by a physical system that's emitting wavelengths of light. The spectrum of delta is this set of numbers that happen to be non-negative. And so it's very tempting to ask, there are definitely ordinary garden variety square roots, real square roots of these numbers. And the question is there a square root of the operator, delta? Okay. So what would that mean? What would a square root of delta mean? It would mean some weird operator, and it's not going to be that weird at all, actually, but in general it can get a little bit weird when we go further. Some operator d, and again, this is something that is a machine that takes a function, that's supposed to be a set brace, and spits out a function, such that if you take d twice on y, you get delta of y, or in other words, minus y double prime. Okay. Now, this is a great place to stop the video and guess what that operator is, because this is really, so far, a total recap, just in a new language, of what the basic ideas we were doing. Okay, so first of all, this is the second derivative. This is built out of doing something twice. So d is just going to involve a first derivative. The only thing weird is the minus. Okay, now I put in the minus sign artificially, it seems, but the thing is that putting the minus sign in here, so let's go back to where we've never heard complex numbers before, right? If you don't put the minus sign in here, then the spectrum here is not non-negative numbers. It'll be non-positive numbers. And then if you've never heard of complex numbers and somebody says, can you take the square root of this guy? Well, it's not so hard to prove that the spectrum of this square root is going to be the square roots of these numbers. And if you've never heard of the square root of a negative number, then you're not going to accept that. So we fix it by putting the minus sign here. Okay, but unfortunately, well, I don't know, fortunately, because the complex numbers are cool, even though that makes it more plausible that there should be a square root, it can't just be the first derivative operator, because that's not going to reproduce the negative sign. So one way or another, you're forced to deal with i's, of course. And the answer, of course, is that dy is just iy prime, because then d of dy is I times iy prime prime, and that's minus y double prime. Okay, so this is a very sophisticated way, because it gives us access to some very cool concepts that I'm going to touch on in a minute, of saying why we had to introduce i's in the first place. That the square root of this operator, and the delta here, let me give it a name, this is the mathematician's version with this minus sign. It's the one-dimensional version of the Laplacian. And I'll talk about the n-dimensional version, certainly the two-dimensional version, in a little bit. And if you've ever seen the Laplacian, you recognize that it's about second derivatives, but the minus sign may look unfamiliar. Well, the mathematician's Laplacian has the minus sign incorporated, and because mathematicians love operators with a positive or at least a non-negative spectrum, they're just nice, really nicely behaved. And what we've done is we've taken the square root of the Laplacian, which is just nice to say. And say, you could say that at a cocktail party, right? I took the square root of the Laplacian today. It was cool. Okay. Now we did it in one dimension, and it wasn't super, super deep or anything. It's really just first derivatives, except, wait a minute, it is kind of deep if you think complex numbers are deep. It's another way to think about that I having to come in. Okay. So, and we need, so what do we need? We need y, if we think about the kinds of functions we actually get here, right? What is the spectrum of this? What are the eigenfunctions and eigenvalues to take dy equals lambda y, or in other words, I prime equals lambda y? Well, that's basically back to our absolute first equation we ever did, but including the I in right from the start. And of course, y of t is then going to be e to the, I think it has to be minus I lambda t. Okay. Those are the kind of functions we're going to get. So we have to have the y's be complex valued functions, and our operator I and the idea of complex math and complex multiplication also shows up in the definition of this operator D. Okay, so at this point, it's probably the world's most unnecessarily sophisticated way to introduce I as a device for taking the square root of the Laplacian. But we'll see that it has a wonderful, very cool generalization in the next video.